As for the Malthus model, the aim of the logistic model is to describe the time evolution of a population of individuals. The Malthus model is actually the simplest possible of this type of models. So if you don't know about this model, I warmly suggest to watch the video we realized on it. You can find the link in the description. In Malthus model, an extremely simplificatory but at the same time unrealistic assumption is made. And this is the growth rate of the population is constant. Let's refresh what is the growth rate. Suppose that we have a population whose size is described by numbers Pn. So Pn is the size of the population at time n. We consider the variation of size between two consequent times, so Pn plus 1 minus Pn, and we compare this to the total size of the population at time n. So we construct this ratio, Pn plus 1 minus Pn over Pn. This quantity is what is called the growth rate of the population. Now, the key point of the Malthus model is that this quantity is independent of everything, so in particular, is independent of n and of the size of the population Pn. Now, this is quite unrealistic because if, for example, we take real observations of a certain population, like, for example, population of humans on our planet in the previous century, we can observe these values and we can see that they are never constant. They change in time. So, first of all, in real models, we don't see the Malthus assumptions. Second, it is in general a reasonable assumption to think that R should depend on time directly and indirectly through the value of the population Pn. For example, if we think to a pandemic is an event that happens at a certain time independently on the size of the population. So that's why we should have that R depends on n, and the size of the population itself should affect R, because a larger population will mean that if the food is the same, there will be less food for everyone, so it will be harder to survive, and therefore the growth rate will be smaller. So we may expect that this rate depends on Pn. The logistic model does a step forward in this direction, assuming that R is a function of the size of the population. So we neglect the effect of dependence on time, and we focus only on dependence on size of the population. And this function R of Pn should verify two important conditions. The first one is that this function should depend in a decreasing way from P. So higher is P, smaller is R. And the second condition we want to obey is the following. We want that there exists a sort of maximal size for the population beyond which the growth rate becomes negative. A negative rate means that the population is going to reduce. So let's say that population is forced to reduce in that case. Now, if we think about how a function of this type could be made, we could say that if we plot a diagram where we see on the abscissas the values of population and on ordinates the values of growth rate, so marking somewhere the maximal threshold capital M, basically these two conditions means that the function R of P is decreasing. It is 0 at M and negative beyond M. So any function of this type is a function that fulfills this condition here. Now, among all the possibilities, the simplest are those provided by straight lines, like this one. In this case, the function R of P is of type, let's say, AP plus B. Instead of writing that way, I want to write it in a different way to emphasize the fact that when P is M, the rate is 0. So I consider factor P minus M first. In this way, I have a factor that vanishes when P is M. Now, if R of P is this one, this is an increasing function of P. That's why I have to put a minus here. And if I want to change the slope, which is now 45 degrees, I need to put a factor here. So this is now the shape of how R could depend on P in the simplest possible way, respecting these two conditions. And this means that once we plug this into the model, we get this equation, Pn plus 1 minus Pm divided Pn is equal to minus K times Pn minus capital M. Now, by a little work of restyling, you can easily see that this identity can be written in this form, Pn plus 1 equal minus K, or plus Km minus Pn times Pn. And under this form, it is usually written the logistic model. This diagram represents the evolution of the first 60 values of Pn generated by the logistic model. In particular, in this figure, we are treating the case r equals 0, which is particularly simple because when r is 0, the right-hand side here is 0, so Pn plus 1 is 0 for every n. So apart from the first element of the sequence that could be positive, the population is equal to 0 from time 1 to infinity, we may say. Now, what we are going to see is a sort of animation when r ranges from 0 to 4. For each value of r, we will represent the sequence of dots which are values of Pn. So different r, different sequence Pn. Here, as you will see, we are between 0 and 1 with r. The sequence is decreasing and rapidly decaying to 0. So we may say that for these values of r, the population is rapidly going to the extinction. As you can see here, r is changing at uniform speed. The line of the dots is moving a little bit, but let's say that a little change in r produces just a little change in the evolution of these dots. Here we are above 1. Now something new happens because the sequence is still decreasing and attains in the long time a positive level. So in this case, the population is not going to the extinction. And as soon as r increases more and more, as you can see, the behavior of this sequence changes because it is like if the long time level grows, and so at certain point we will have that the sequence of Pn will become an increasing sequence. This is more or less what happens until we reach with r the value 2. Above 2, let's say that long time behavior does not change too much. So we see still a long time constant value for the population. What changes is in the how we obtain this long time behavior. This will be more and more clear. It's a sort of oscillatory movement up and down for the values of Pn that will become more and more evident. And these oscillations are damped oscillations, okay? As you can see from this, figure here, you see the oscillation up, down, and they reduce in amplitude. As soon as r approaches 3, these damped oscillations are going to enlarge more and more. It is like if this sequence of dots is going to open into, like here, 2 sequences of dots. This means that here, for example, the Pn is going up and down between these 2 values. So is no more, we cannot say that in long time there is a constant value for the population, but rather the population oscillates between 2 values. And here in the next values for r, here we have an oscillation between 4 distinct values. As soon as r crosses a certain critical threshold, the behaviors change dramatically. As you can see here, it seems like if points are moving in a crazy way, in a chaotic way. What is going on here? You see a little change in the parameter R now produce a dramatic change in the sequence Pn. So when I change a little R, the sequence Pn changes a lot. So this means that if you imagine that this is a real-world problem, you know, parameters are just estimated from something, so they are subject to errors. And this means that if you consider errors, a little error here could produce a completely different behavior of Pn. So in other words, it is hard to do predictions when R is big in this model. This is now a picture when R has been fixed to 3.97. And here you can see a second feature of these dynamics. So here R is fixed. You see that the movement of Pn is of type up and down, touching values in middle here, with apparently no regularity. So it's hard to see what is the behavior after n equals 60 in this case. So it's hard to do long-time predictions here. So this is a prototype of what is called a chaotic system. And in particular, these two features of this system, the sensitivity on R and the unpredictability on long time in N, makes this an ideal tool to construct random numbers. So in conclusion, we can see that between Malthus model and logistic model, there is a dramatic difference. In Malthus model, we have just three possible behaviors: an exponential growth, an exponential decay to the extinction, or a completely stationary behavior. Nothing happens, a constant behavior. Here, in logistic model, we have many, many more possibilities. We have an exponential decay to the extinction and the decay to a positive quote, as well as an increasing reach of a stationary equilibrium, and also a sort of oscillatory with damped oscillations way to reach the equilibrium. We have seen also periodic movements between 2, 4 values. It is possible to prove that even larger periodic movements are possible. And finally, a completely chaotic and unpredictable behavior. That's why this system is much more complex than simple Malthus system.